talk about the need for modulation. So, the frequency of the human voice ranges from about 100 to 3000 Hz. Your voice can make sounds from low to high frequencies, kind of like a piano, and these sounds have numbers called frequencies. If those frequencies are transmitted directly as radio waves, the interference will cause them to be ineffective. Since radiation is poor and the signals get highly attenuated, so if we send your voice directly through the air like magic, other sounds can mess it up and it becomes very weak and hard to hear. This means baseband signals cannot be transmitted directly over long distances, so we can't send your voice very far just by itself. Modulation tends to increase the frequency of the signal about to be transmitted, and hence modulation tends to increase the frequency of the signal about to be transmitted, and hence tends to increase the distance over which the signals can be transmitted. We put your voice on a faster wave, like giving it a piggyback ride, so that it can travel farther. For efficient radiation, antenna dimensions have to be of the same order as the wavelength of the signal being radiated. To send the voice on a fast wave, we need a big antenna that's the same size of the wave. Given the frequency f and the wavelength lambda of an electromagnetic wave, the velocity v is given by what is below. So there is a math rule that tells us how fast waves go based on their size and how often they wiggle. And this is the formula. V is equal to f lambda. Thus, for an electromagnetic wave of audio frequency of say 3000 Hz traveling at the speed of light, then its wavelength is going to be given by this. Lambda is equal to c on f. If we use a sound wave of 3000 numbers and it moves as fast as light, we can figure out its size. From the results, it's obvious that it's virtually impossible to transmit low frequencies, since the required antennas for efficient propagation would be miles (kilometers) in length. If the wave is too slow, the antenna we need would be as long as a really big road, which is not possible to use. On the other hand, considering a modulated signal with a frequency of 5 MHz in the broadcast band, but if we put your voice on a super fast wave like 5 million wiggles, it is much easier. Wavelength will be hence the height I of the half wave. Wavelength will be hence the height I of the half wave antenna will be. I'm so sorry for the mistake. Wavelength will be lambda is equal to c on f, which is equal to 3 times 10 raised to the power 8 on 5 times 10 raised to the power 6, which will be 60 meters. Hence the height L of the half wavelength will be 30 meters. That is a realistic height, and the antenna can be installed. Now let's talk about transmission. The transmission of one signal at a time. The transmission of one signal at a time on a channel is a highly wasteful situation. Sending just one message at a time is like sending one toy car on a big road. It wastes space. By the use of modulation, several signals can be transmitted at a time on a channel. With modulation, we can send many messages together, like sending a lot of toy cars on the road. This is referred to as multiplexing, which is a means which allows two or more signals to be transmitted simultaneously over a channel. This is called multiplexing, and it means we can send many messages all at once. This increases the efficiency of the channel. This way, we use the road better and can send more messages faster. Let's talk about this diagram here, which goes into the classification of modulation. The modulation process is classified into continuous wave modulation and pulse modulation. And the types of modulation, we have the continuous wave and then the pulse modulation. So, under continuous wave modulation, is divided into amplitude modulation and angle modulation. And under angle modulation, we have frequency modulation and phase modulation. Now, under pulse modulation, we have digital modulation and analog modulation. And under digital modulation, we have pulse code modulation. And under analog modulation, we have PAM, PDM, and PPM, which we'll discuss further. Imagine you have a toy car that moves back and forth in a straight line. The car represents our carrier wave. The car's speed, how fast it moves, changes over time. That's like the equation V of t is equal to A sine omega t plus phi. Now, let's go on. V of t is how far the car moved at a specific time. A is how big the car is. Omega is how quickly the car goes back and forth. And phi is where the car starts from, or its initial position. So the car wiggles like a snake, and we can use this wiggling to send the message. Now let's talk about amplitude modulation, which is AM. You imagine you have a flashlight. The brightness of the light changes when you talk into it. That's AM. The flashlight's brightness, how strong the light is, depends on your voice, the message. We can use this brightness to send music or talk to someone far away. Frequency modulation, on the other hand, is like, think of a swing in a playground. When you push it harder, it swings faster. Frequency modulation is changing how fast the swing goes based on your voice or music. So the swing swings differently to carry different sounds. Phase modulation. Imagine you are playing with a spinning top. Sometimes it spins clockwise and sometimes counterclockwise. Phase modulation is like changing the direction of the top spins, using your voice or music. The top dances differently to share different messages.